very good morning and welcome you all to this NPTEL course on electrical distribution system analysis. And we'll be talking about traditional approaches of VVC. During the last lecture, we have discussed in detail what are the issues due to variation in voltage being experienced in distribution system, how that can be minimized, and different compensation techniques. Now today, we'll be talking about what is VVC. So the primary goal is to maintain acceptable voltage levels along the distribution feeder under various load conditions. Imagine we have the source, maybe substation, bus 1, bus 2, bus 3, and we have different loads connected at different buses. Now we are very clear due to the basics fundamental of physics, having resistance in the conductors, the voltage experienced in different buses as you go away from the substation will experience low voltages. Now the target is how to make sure that the voltage drop is not very significant so that the equipments connected to my different zones or areas or the buses are not going to get damaged. And hence it is important to maintain acceptable voltage levels along the distribution feeders under various load conditions and ensure voltage stability both under full load as well as light load scenarios. Now, how do we do it? How do we achieve it? Because the loads are keep on changing, the voltages have to experience, a different way. So, utilizes individual, independent and standalone volt var regulating equipments where substation transformers load tap changes, so-called LTCs, line voltage regulators, fixed and switched capacitor banks. So these are the methods through which a reasonable voltage balance across the system can be achieved. Now, based on local measurements of voltage and currents, we can determine appropriate control action for associated devices like OLTCs, transformers, step voltage regulators and capacitor banks. So we need to understand how they need to be operated. Now, in case of standalone controllers, which employs the basic volt var control to achieve feeder voltage within acceptable limit and also to improve power factor at load locations. Now, what are the advantages of having standalone controllers? Economically feasible with low cost implementation, no need for field communication, scalability in terms of deployment is possible. Now, VVCs is a fundamental operating requirement for all electric distribution system, integral to maintaining system reliability and efficiency under varying operational conditions. Now, for the benefit of the viewers, what I like to highlight, this kind of infrastructure is not existing in our rural distribution system. Most of the cases, such kind of control mechanisms are present in case of modern distribution systems, and hence you might have experienced in rural areas during evening hours, during peak load, the voltage drop for the residents living very far away from the substation do experience huge challenge even to switch on their tube lights. Now, let us focus on what is OLTC. Now, the OLTC, which is on-load tap changer transformer, provides tap terminals for turns ratio, control within your transformer, enabling changes in the transformer ratio by altering the amount of winding in the circuit. OLTC allows for this adjustment without service interruption, making it more complex and expensive than no-load tap changers, that is NLTC. Now, two main designs, one is known as reactance and the other one is resistive type OLTCs. Commonly employed in conservator type transformers, seldom in hermetic transformers, allows for a regulation change of plus or minus 10% of rated output voltage with 16 taps above and below the rated voltage, each adjusting the voltage by an approximately 0.625 percentage. Means the number of steps we do, 0.625 multiplied number of steps n will give you the amount of voltage being actually adjusted or managed. Due course of time, we'll see a small numerical also to make sure how these tap changes are going to manage the voltage profiles. Typically, core type 3-phase transformers equipped with the gang operated LTC, synchronizing tap position changes across all three phases in case of 3-phase transformers, operate typically within a plus or minus 10% range of the regulated voltage with discrete level adjustments. Now let us focus very carefully on this example. A transformer which has a rated output of 120 kilovolt, if the tap changer is used to decrease the voltage by 4 positions and each tap position alter the voltage by 0.62%, what is the new output voltage? Now quite simple, let us calculate. The new output voltage will be 120 kV minus 120 kV times each step will help you a reduction of 0.625% change in voltage, and there are actually 4 position change. So finally, the net output voltage will be 120 kV minus 3000 will be 117 kV. So this is how actually you can control the voltage using LTCs, that is your on-load tap changer transformers. Now let us physically focus on on-load tap change transformers. Tap changing modes can be performed either manually or automatically. The purpose is to maintain a consistent voltage profile across the entire network. Now the advantage of OLTC is to ensure continuous and stable power supply during tap changes, offers flexibility and reliability in voltage regulation, especially in dynamic load conditions. Now, what is AVR controlled OLTC? The OLTC is automatically controlled by the AVRs, which monitors and maintains the voltage within a specified range. Now, automated voltage regulation, when the voltage deviates from the permitted range, the AVR detects this change and commands to the OLTC to adjust his taps automatically to restore the voltage to the desired level. Means you, instead of 1 per unit, when you experience 0.95, and if you want it to go from actually back to 1 per unit, that signal must come from your AVR so that OLTC can react or act upon. To minimize the impact of transient voltage variations and stay within the deadband, an adjustable time delay is employed. This prevents unnecessary tap position changes in response to brief voltage fluctuation. Imagine if you experience a spike or a sudden voltage change at a given point of time, and that is not going to stay for a quite long time, okay? So probably you need not act or force your OLTC to react under the circumstances. So if it stays for a long time, probably after that the signal can come to OLTC to react accordingly. Now the role of a line drop compensator, the LDC, assists in regulating voltage at a distance bus from the OLTC by mimicking the voltage drop across the feeder. Now voltage boosting, by simulating the feeder's voltage drop, the LDC enables the OLTC to increase the voltage at its output, ensuring that the correct voltage level is maintained at the load. Considering a feeder, my substation, and this is bus number 1, 2, 3, 4 buses with different load currents I4, I3, I2, I1, and the impedances of Z1, Z2, Z3, and the voltages are V bus, V1, V2, V3 and V4. Now If you are interested to know what is V compensation, which is V bus voltage minus the drop in the first feeder, which is Z1 I2, second component Z1 plus Z2 I3, then Z1 plus Z1, Z2 plus Z3 times I4. So this is what the voltage need to be compensated. So if you see the approach of a OLTC and AVR mechanism, so you have a reference and then you have the V compensation which has been calculated for the feeder from time to time, because I1, I2, I3, I4 is not going to be constant, and probably that can go to your tap changer command to react. Now OLTC control, similar to a 66 by 33 kV substation, then 33 by 11 kV substation, and finally your load point and a DG connected. And you could see the voltage profile, how they are going to change for peak loads, off-peak loads, for DGs, load with DGs, and off-peak hours, off-peak load with DG. So you can see there are different profiles. You can see how the voltage profile is keep on changing in a distribution system. And in few cases, in case of off-peak load, you could see the voltage profile is keep on increasing, because when the load is less, so probably you can experience reasonably higher voltage at the load point. However, in case of peak load, the voltage drop drastically, and but off peak load also it drops. But in the previous case, we had a distributed generation, so that energy which is available to you even during off peak can help you to uplift the voltage profile slightly, because there is an injection of power that may help the voltage profile to increase. So this different load profiles will give an idea, because of the peak load how the voltage drops, and because of the off peak how the voltage drop not so significantly as compared to peak load. However, when you connect a DG even during off peak, the voltage profile actually can slightly be improved at the terminal point. Now the step voltage regulators, SBRs. SBRs are specialized devices used for voltage control in power systems, consisting of an auto transformer with adjustable taps in the series winding, allowing for dynamic voltage adjustments. Now, these devices offer a regulation range of plus or minus 10%, divided into 32 steps, with each step enabling a 5 upon 8 percentage change in voltage, and probably 5 upon 8 is nothing but your 0.625 percentage that we have discussed earlier. And this allows for precise voltage adjustment either by boosting or bucking the voltage at the regulated bus. SBRs are designed to operate under load conditions, enabling real-time adjustment to the taps of the series winding to maintain desired voltage levels even during fluctuating demands. They can be strategically located at various points in the electrical network, such as substation or along feeders, to effectively manage voltage levels across the system. SVRs are adaptable for both single phase and three phase systems. Single phase SVRs address unbalanced voltages and phase specific loads, while three phase regulation can be achieved by connecting single phase SBRs in configurations like Y, delta, or open delta, or by using a dedicated three phase SVRs. Now the physical device, the SBR, how it look like, and normally it is mounted on the poles. Now AVR and automatic voltage regulation, the SVR uses automatic tap changing, responding to inputs from potential and current transformers, that is PT and CTs, to maintain a predetermined output voltage at either the output terminal of the regulator or a remote node on the feeder. Now, voltage regulating relay and bandwidth, the system includes a voltage regulating relay, so called VR, set to a desired voltage level at the load center. The voltage is allowed to fluctuate within a specified bandwidth around the set point. Now, tap changing triggered by voltage deviation. When the measured voltage deviates by more than plus or minus half of the bandwidth from the set point, then the regulator changes taps to correct its voltage. A time delay is implemented in the tap changing operation to prevent unnecessary adjustment due to transient or short term variations in current that we have already discussed. And finally, the line drop compensator LDC boosts the voltage at the regulator output to compensate the voltage drop along with the feeder, effectively regulating voltage at the load rather than at the regulator bus. With R and X setting in the LDC adjusted to match the feeder impedance. Now you can look into the SBR control mechanism. This is your supply voltage, and then you have step voltage regulators, PT, CT is connected, and this is your SBR output voltages, and this finally the load voltage which has been experienced. And there is a algorithm that for your SBR control can be incorporated within the control strategy. Now, if you look into the voltage profile, how it is keep on changing. So, let us imagine this is your substation voltage, and there is a primary feeder, okay, and finally you have a DG, for an example a PV system, and through SBR you can experience how the voltage profile is keep on varying through adjustment, and finally, so that means there is a drop and then you compensate, there is a drop and then you compensate. The target is actually the primary line should not consume or force your load bus to experience severe voltage drops. So this is how actually the SBR tap determination at this point of time. This is SBR tap operation, and different level again determination and operation, finally determination and operation. For each time scale, you can determine the SBR tap position, and then you take action so that you uplift, you determine, and then uplift, you determine, and then uplift. A shunt capacitor, which is a popular device known to all of us, they are used for a voltage improvement, voltage profile improvement. So, shunt capacitors inject reactive power into the electrical system, improving efficiency by reducing losses, freeing up capacity and correcting power factor as highlighted in IEEE 1036-2020. Now, these devices connected in parallel with the load modify the network characteristic through capacitive reactance and offer advantage in terms of low cost and installation flexibility. So, this is one of the cheaper combinations, cheaper device, a cheaper solution I can say, which can be achieved through shunt capacitors. The discrete switching on or off of capacitor banks provides local reactive power and compensating inductive loads and improving the power factor closer to unity, particularly near the load point. By reducing the total current in the feeder, shunt capacitor relieves the system of wattless current, thereby reducing I square R line losses and releasing feeder capacity. The injection of reactive power by shunt capacitor not only reduces voltage drop, but also assists in maintaining local voltage levels within allowable limit, contributing to overall voltage stability in varying load conditions. As bank of shunt capacitors, I mean this is a very huge setup. So probably this is how it looks like, probably a bit of higher rating. Switchable shunt capacitor, which is an interesting device where instead of discrete switching, probably we can have a bit of continuous switching, are equipped with local controllers that switch capacitor banks on or off based on the minimum or maximum value of the specific parameters. For voltage control, a voltage relay activates the capacitor when the voltage falls below a minimum threshold and deactivate it when the voltage exceeds a maximum threshold. Means when the voltage drop from 1 per unit to 0.95 or 0.9, then that activates, and when it is close to 1.1 or 1, then probably that deactivates. To prevent excessive switching operations, time delays and bandwidths are incorporated into the control mechanisms. When focusing on power factor correction or minimizing losses, the system monitors the load kVR, reactive power, or total current as a basic for its control. The control system for automatically switching shunt capacitors generally consists of a master control relay, time delay relay, and control switches. This mechanism is similar to the time delays and dead bends used in OLTC and SPR equipments. On feeders with predictable daily load profiles, time control capacitors are particularly useful, being switched according to a fixed schedule to time the varying demand for capacitor kVR's reactive powers. And finally, moving to the control of volt var flows in relation to a distribution primary line using a traditional VVC approach standalone equipment. The setup, you can have a look, and this is my distribution primary line. You have actually current voltage sensors at both the terminals, and you could see the capacitor banks are in place. And this is my voltage regulator, and you can experience the standalone controllers at both the terminals, and based on which you received a on and off control signal, control command to the capacitor banks to operate. And similarly, you can get a on and off control signal to your voltage regulator also to operate. Bidirectional power flow, which is a very common scenario due to presence of distributed generations. So due to the presence of distributed generation at the load point, so probably the load may consume energy, and sometimes if it is in excess beyond the load, then the DG start penetrating energy towards the substation. So bidirectional power flow is an interesting scenario due to presence of DGs and can lead to high or low service voltage problems impacting operational schemes. Now, what are the issues and challenges? Lack of coordination between volt var devices, that is OLTCs, SVRs, and capacitor banks, and which cannot be make optimal operation. Absence of self-monitoring, essential for detecting out-of-service capacitors. Inflexibility in handling feeder reconfigurations, and operators' inability to override control actions when necessary. So these are the challenges we normally face because of shunt capacitor control mechanisms. Thank you very much for your attention.